One of the trickier limits to show when you're first introduced to the epsilon delta formalism is something like x squared. So if we take the limit as x goes to 3 of x squared, we should get 9, of course. But showing that with epsilon delta can be a little tricky. But we can approach it in the same sort of style that we would do a normal function and deal with x squared minus 9. And of course, our objective is to make this guy small. We want it to be less than epsilon by the end of our argument. Okay, and we can notice that this is going to be a difference of squares, so I can factor that as x plus 3 times x minus 3. And as is typical in an epsilon delta, that x minus 3 can be made small. It can be made less than our delta of choice. But how do we deal with x plus 3? The idea is if we can control how large it grows, then we can use our x minus 3 to control the size of x squared minus 9. So notice that as x approaches 3, x plus 3 should approach 6, of course. So maybe the idea is x plus 3 can be bounded near 6 somehow. Okay, well, indeed, if we demand that x minus 3, sorry, x minus 3 be less than 1, say, then x minus 3 has to be less than 1 and greater than negative 1, just getting rid of the absolute values. And the trick is to add 6 everywhere. So that means that x plus 3 is larger than 5 and less than 7. So we found our bound, our upper bound for x plus 3. And that greater than 5 is helpful because it guarantees us that we can get rid of our absolute values, actually. So, to sum up, if x minus 3 is less than 1, then x squared minus 9, we can factor it out. But that x plus 3 term in absolute values is just x plus 3 without the absolute values because it's greater than 5. And that's less than 7 from what we just showed. So we can go back to our factoring x plus 3 times x minus 3, but that's going to be less than 7 times x minus 3 because that x plus 3 term is less than 7, of course. Okay, now it seems like we're making progress. So if we can just ensure that x minus 3 in absolute values is also less than epsilon over 7, then that guarantees us our results. So in other words, we need that x minus 3 be less than 1 and x minus 3 be less than epsilon over 7 simultaneously. We needed to have them both at the same time to get both of those inequalities. Okay, we can accomplish this by setting x minus 3 to be less than the minimum of 1 and epsilon over 7. Because if it's less than that minimum, then it must be less than both of them. So now we can go for our proof. So proof, let's let epsilon be greater than 0, and we'll let delta be the minimum of 1 and epsilon over 7. Okay, then if x minus 3, x minus 3 is greater than 0 and less than delta, then x squared minus 9 can be factored as x plus 3 times x minus 3 in absolute values. That's less than 7 times x minus 3. We saw above that that's because x minus 3 is less than 1. But that's also less than 7 times epsilon over 7 because x minus 3 is also less than epsilon over 7. Okay, but that's our epsilon. So that's exactly what we wanted to show. So in other words, the limit as x goes to 3 of x squared is 9. And that's it.